Hi, I'm here at GTC at the NVIDIA booth with Gilad. He's one of the head people from Mellanox who transitioned over to NVIDIA, and he runs the optical networking group here with Spectrum X and the co-package Ethernet Photonics. Nice to meet you.
Nice to meet you too.
In optics.
Yeah, I'm working on the networking product.
So the biggest question on everyone's mind is copper versus optics. That's all my friends talk about. Is it laser? Is it copper? I'm a big believer that there's a place in the world for both, and you have to use the copper where it's necessary and optics where you need the data rates that you can achieve. So wanted to get your take about the manufacturability and the scalability, and how do you see the future of AI networking and computation with the products you came out, and then what you have here with CPO and all these other things. So take it away.
Sure. So first, you're right in the sense that everywhere you can use copper, you want to use copper. Everywhere you can use copper. And the reason is that copper consumes zero power.
Right.
And it's very reliable, very resilient. So if we can use copper, we use copper. That's period. Now, copper is limited in distance. So you're kind of limited on where you can use it.
Right.
Today, we are using copper for scale up, because scale up is contained in a rack, for example, NVLink 72,
Right.
that covers the distances that we need, and we're using copper. Power is the key element that determines what will be my compute capacity in a given data center.
Right.
So I want to do everything to optimize compute to power,
Right.
and means that I want to minimize power wherever I can. Copper is one good option to do that. Now, when I cannot use copper because the distance is too
Far.
from copper, then you need to use optical interconnect.
Right.
Now, in optical interconnect, in the traditional usage of optical interconnect, the connectivity is based on transceivers. And there are different kinds of transceivers. There is everything from full read to half to linear pluggable, for example. There is DR and FR and so forth. There is a variety to cover different distances and different combinations of lanes, and with DSP, without DSPs, depends on if it's going to be a design that requires more power to go to for the signal to go, less power and so forth. But they are all consuming power which is much greater than if I would take that optical engine that translates light to electricity and put it as close as I can to the network device.
Right.
This is what co-packaged optics is. Now, co-packaged optics, the idea about co-packaged optics is not new, because it was tried multiple times in the past, but it was not done right. It was not done right. When we start to see that optical interconnect becomes heavier and heavier element, or bigger and bigger element in the data center, and scale out is something, it's the first infrastructure to actually see that.
Right.
Because it's fully dependent on optical connectivity.
Right.
And the amount of connections that you need to have on scale out is doubling from GPU to GPU generation.
Right.
And the sizes of infrastructure are growing. So that's actually, it's something that will see a lot of power. And it says, okay, we want to bring co-packaged optics to that infrastructure, but we want to build something that is reliable, effective, manufacturable, and can go to mass production and give us everything that we want.
Right.
So we did several things differently than the previous attempts. First is that we had a new architecture for optical engine. Other attempts were using MZM, we're using MRM, microwave modulator, smaller engine, scale out the high radix switches. We want small engines that can feed the high radix switches, so that's one thing. The second thing is we needed to have a good packaging technology that to validate everything. This is where we work with TSMC and created a new packaging called COUPE.
Right.
So that was the second thing. The third one is how do you do alignment of fibers and optical engines? You can do side alignment, you can do full alignment, there is different ways. And we didn't want to take the simple approach that is not validated or you cannot validate it. We actually did the full alignment, for example. So we did things differently, understanding that this is how we could build something that is robust and can go to full production. And that's what we did in NVIDIA co-packaged optics. We also needed to make sure that we're bringing the ecosystem with us. because there's going to be a lot of capacity being built. We wanted to invest in our partners so they build the right technology to our specification. That there is an element that we can buy from multiple bases and so forth. So this is where we make investments and
Momentum and coherence.
just an example, but we're working with a good amount of partners and ecosystems. Every place from packaging, laser sources, fiber arrays, so forth. So actually a very healthy ecosystem. And now we are going to production with co-packaged optics on scale out on both spectrum X and quantum X. Now the next phase is going to scale up. And the reason to go to scale up is because the scale up domains are increasing in size. Today we're doing 72, for example. So it's covering the reg use, copper, great option for that. When we're going to transition to Feynman from a roadmap perspective, in Feynman we want to do 1152 scale up GPUs, and that's not something that you can do in a proper distance. That means it goes optical, and if it goes optical, and in scale up there's 10x the bandwidth compared to scale out, we're talking about much larger capacity of connectivity between GPUs. Obviously, we want to use co-packaged optics there. So this is where we announced that for generation, we'll also have an NVIDIA co-packaged optics.
So it's more of like a 2028 story.
I think it's marked at 2028 on the slide that was presented yesterday in the Jensen.
Very cool. So that's the Spectrum X Ethernet photonics right there.
Correct. So you see that in the middle there is the Spectrum X, Spectrum 6 ASIC. It's 100 per second switch. And then surrounding it, you see all the optical engines that exist there. And those optical engines are connected to the fibers that come from the switch, as well as connected to the laser source, or the lasers, because they need the light source actually to drive the signal in and out.
It's very, very impressive, very interesting engineering. Never seen anything like it. And I think this is one of the underappreciated aspects of this whole extreme co-design ecosystem of what NVIDIA has with not only the processor, but the networking to move the data and the memory fast enough to build that coherence to reduce the latency and how things are processed. Thank you so much for your time.
Thank you very much.
Have a good rest of the show.
Thank you.